Hallo, it's dumplet here. Here's an item on number theory. If the base 10 number, as you can see on the screen, is expressed in base 7, what would be its last 3 digits? Now this item came from the DAM 2022, an examination that Dumplet has hosted. The link to the PDF file will be in the description. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Now, whenever we have an item like this one, we have a base 10 number with like binomial coefficients, and seemingly there's a pattern here. We typically try to consider a GF that is called the generating function. Okay, now we're just gonna focus everything on base 10 before we move on to focusing on converting it to base 7. So before we try to find out what function kind of generates this sum, let's try to find a pattern first. Now, based from here, I think I have powers of 4, or which is essentially powers of 2 as well. And then I think I have like a bunch of 2022 choose evens. And well, 4 is 2 squared, 16 is 2 raised to 4. And pretty interestingly, well, 2 raised to 0, technically, I could add that in here. And then the 2 raised to 2022, it can technically be multiplied to this one, I guess. So we could have we could have a sum with the pattern. So 2 raised to 0 times 2022 choose 0 plus 2 squared times 2022 choose 2, and then just all the way until the last one. So 2 raised to 2022 times 2022 choose 2022. Now, the generating function really is just involving the binomial expansion of, in this case, it's going to look something like 1 plus x, right? This is not really the same thing, but 1 plus x, in this case, for example, if I raise to 2022, it's going to give me something similar. So the first term, it's going to be just 1 raised to 2022. Well, that's just 1 anyways. So it's just going to be 2022 choose 0 plus x times 2022 choose 1 plus x squared. So if I were to really expand this with the binomial expansion, I will get something like this. So we're going to use this to kind of help us reach this sum, because this is kind of similar, not really exactly the same, but very similar. And then we're just going to do some manipulation to generate that sum. All right. So with this idea, I'm going to expand two binomials over here, the 2022nd power of 1 plus x and 1 minus x. And as you can see in this kind of short demonstration I did, for the minus case, for the 1 minus x case, the only thing that's different is the alternating signs. So plus minus, and so on, that's just going to be the difference here. So taking a look at the things here, for all the terms with 2022 choose evens, apparently the sign is always positive, right, for both. So it's technically a positive sign for both all the way until the end. But for the ones with 2022 choose odd, they're going to have different signs. Now, this is particularly interesting for us because if we add the two, for example, if I add these two equations, the terms with the binomial coefficient 2022 choose the odd numbers, it's going to cancel out. So that's going to be the motivation here. So let's try to add these two. And well, if I add these two, we're going to have two of these, like two of these, and two of these. So let's just not have duplicates. Let's just divide the result by 2. So what I'm going to do is 1 plus x raised to 2022 plus 1 minus x raised to 2022. We're just going to divide this by 2. And then we realize that this will be equal to the first term. Well, all the 1s technically, all the 1 raised to anything, I'm just going to replace it just with 1. So the first one is just going to be 2022. Choose 0. All right. The next term will be x squared times 2022. Choose 2. And then the pattern will continue all the way until the end. All the way until x raised to 2022 times 2022. Times 2022, choose 2022. Now, this is the pattern, or the sum. We just kind of altered it to kind of have a pattern here. And compare this one with this. Essentially, I could just add an x raised to 0 in the front here. So compare these two. Essentially, they are the same. It's just that x will have to be equal to 2. So what we have to do is simply evaluate this at x equals 2, because, well, from the start we kind of wrote the given sum to be something different, just to have more of a pattern here. And then we realize that this is the function that kind of generates this sum. So we just have to put x equals 2, and this part would be exactly the same as the given sum. So let's try to substitute 2 into here. We have 1 plus 2, so this was the x. These two were the x's before, but after we substitute x equals 2, we're going to get this one. So essentially, this is the same as this one. And then we simplify this one, it's going to be 3 raised to 2022 plus negative 1 raised to 2022. Well, that's just equal to 1. And then divided by 2. So this is the base 10 representation of this number. Now, we want to find the remainder. We want to find the last 3 digits of this number in base 7. Now, in base 10, the numbers that we are typically familiar with, if we want to find the last 3 digits, we're going to take mod 10 cubed. Because we want the last 3 digits, we're going to divide by 1000 and take the remainder. Now, since we're working with base 7, we're not going to use 10 anymore, but instead, we're going to take mod 7 cubed. So in this case, we're going to divide by 343. And the rest is just an exercise, just a modular arithmetic exercise. So let's multiply both sides by 2, because there's a fraction here. So 2k will be congruent to 3 raised to 2022 plus 1 mod 686. So we have to take this one under mod 686. Now let me just focus on this one. I'll just add the 1 after. So let's try to take phi of 686 first. So phi of 686, that's going to be equal to, well, 686 is just 2 times 7 cubed. So 1/2 times 6/7 times 686. You guys can work out the maths. That's going to be equal to 294. All right, so 294. So 3 raised to 2022. That's the same thing as 3 raised to 294. Right, 3 raised to 294 raised to, I believe it's going to be raised to 6. So 294 raised to 6. We just do the laws of exponents here. 294 times 6, that's essentially raising it to the 1764th power, and then subtract it from 2022. So we just have to deal with the remaining 3 raised to 258, because by the Euler's theorem, well, this is congruent to 1 under mod 686. So 3 raised to 2022 is essentially congruent. So it's essentially congruent to 3 raised to 258. Now it's really just a matter of manipulation from here. All right, the 3 raised to 258, I believe I could just rewrite it as 3 raised to 6 raised to 258 divided by 6, that's exactly 43. And then, well, 3 raised to 6, that's 729. So 729 raised to 43. 729 divided by this 686, that's going to leave a remainder of 43. Right, it's going to leave a remainder of 43. So 43 and then raised to the 43rd power. And then we're just really going to evaluate this thing out. It's going to take a long while because the number is not that pretty. But eventually you guys should be able to get that. This will be congruent to 435 under mod 686. So apologies for a very long calculation, but eventually you should be able to get that. This would be equal to, this would leave a remainder of 435 when divided by 686. Now, let me just continue on from here. 2k would be congruent to, well, 3 raised to 2022, it's going to be 435 under mod 686. So adding 1 to it, it's going to be 436 mod 686. And then just deal with this one. Sorry, k would be congruent to 218 mod 343. And there we have it. We have 218 under mod 343. Now, if you were to answer this, you would still be wrong. And a lot of you guys might have realized, wait, that's not possible in base 7 because 8 is an impossible digit under base 7 because base 7 only uses digits from 0 to 6. So, what's the missing step here? Or what did we miss here is that, yes, we have to convert this to a base 7 number because, this is still technically a number that corresponds to base 10. We just kind of divide it by 343. So we have to convert 218 into base 7. Now, it's going to be a 3-digit number, right? There's a first digit. There's going to be 3 digits. Technically, the 7 raised to 0th digit, 7 raised to first, and 7 raised to second power. So we're going to express 218 as a sum of 7 squared, 7 raised to 1, and 7 raised to 0. Now, we're just going to ask ourselves, how many times can we add, how many times can we subtract 7 squared, or 49 from 218? The answer here would be 4. So we should have here 4. So 4 times 7 squared. All right, so 4 times 7 squared, that's 196. So 218 minus 196, so far that's 22. All right, now 22 is 21 plus 1. I think that's pretty obvious, so 21 plus 1. So that's going to give me this, the 3 here and immediately the 1 here. So 218, if I express it in base 7, it's going to have digits 4, 3, and 1. We're not going to call it 431 anymore, but in base 7, the last 3 digits will be 4, 3, 1. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!